Good afternoon. Today, we'll be presenting assessment task 1B, focusing on the compression and tension results we obtained from our first practical. The aim of this experiment was to determine the properties of aluminium and wood in multiple orientations whilst undergoing compression and tension tests. The desired outcome of this task was to show how different tests applying increasing loads can show the key characteristics of each material, while also displaying how isotropic and anisotropic materials perform differently. The basis of this experiment surrounds a material's capacity to endure and respond to forces induced by stress and strain, shown by these equations. Both stress and strain occur when an object is placed under load, where the overall length changes due to squishing or elongating, creating a relation between this change in length, known as strain, and a force applied through the cross-sectional area this is occurring, known as stress.
Comparing the results of the parallel timber compression test with the theoretical values presented within the Grant Level 1 software, it is apparent that the result is relatable to what should be seen, as the theoretical suggests a yield strength between 1.26 and 3.78 megapascals, while the test provided a value of approximately 3.35 megapascals. Whilst the test produced no direct issues, not knowing the species of wood prompted questioning as to what values should be obtained for the various mechanical properties, as the difference between hard and soft woods can be quite dramatic. From this test, it is suspected that the sample piece is of a hardwood variety, as its yield point was relatively high on the provided scale. From the parallel timber compression test, a result of approximately 24.8 megapascals was produced as the yield strength, a significant amount less than the 36.3 to 62.3 megapascals theorized by Grant's Level 1 materials. The data obtained was much likely much lower than that of the theoretical, due to the anisotropic grain structure of the timber and the prominent growth rings throughout the small cross-section of the test sample that inevitably induced the natural failure. As expected, the results of the compressive test on the aluminium fell within that of the theoretical provided by Granter. Whilst Granter suggested a yield strength between 109 and 439 megapascals, the tested aluminium served to deliver up to 166 megapascals. From the testing of the sample, no challenges were directly visible. A limit was, however, reached when the test sample began plastic deformation, where, as being pressed by the test rig, its cross-sectional area increased and in turn caused the ultimate strength never to be reached. Although falling within the yield strength range provided by Granter, the grade of aluminium and any applied heat treatment process was likely the cause for the resultant observed yield strength being at the lower strength end of the scale.
The data is somewhat in range of the theoretical data, however it was quite a large value of what it is typically known to be. The tensile strength differed by values of up to 45 MPa, whilst also having a yield strength of half the specified value from the Granter software. The challenges faced within the testing were that the jaws were not tight enough, causing the sample to grip and then slip and then grip again. Ultimately, this slipping caused a fluctuation in the final results displayed. Also, with the sharp increases and decreases in the stress on the material and the bumpy trend line after the elastic limit made it hard to compare to the theoretical data. The data may have differed from the theoretical data, as there may have been growth rings in the wood which had caused premature failure, thus making the results not be accurate. To solve this, doing multiple tests on multiple different pieces of wood could explain why the results were not accurate. The timber, whilst having its grain in a parallel position to the test, ended up being the stronger of the tension timber tests. Being that the grain was positioned vertically, it had meant that the shear force would be larger, as the tendency of timber to break with the grain was diminished. The maximal force the timber could withstand was 0.16 kilonewtons, thus implying that timber has much better performance when under compression. However, the timber during the test did not snap cleanly, as the strands of timber grain were left stretched at the shear points. This overall had worked exactly as expected, apart from the not so clear decline in strength that was not visible by inspection. The tested data ended up being close in range of all the aspects from the Granter software, meaning the test went very well. The data may have slightly differed from the theoretical data, as all wood materials have varying properties, as they are a natural material, meaning none are ever the same as one another, making it very hard to compare. The results obtained when inspecting yield strength aligned quite closely with the theoretical data, meaning the test displayed good accuracy. This included a range of mechanical properties, including the tensile strength, which reached 310 MPa, placing it centrally with the theoretical range Granta supplies. The data was not outside the expected parameters of the theoretical data, which is the consequence of the correct clamping methods and accurate measuring equipment. The test was challenging as it was hard to grasp an understanding that the test piece failed even though there was no visible fracture to the metal. The aluminium went through quite extensive plastic deformation and failed without shearing.
In conclusion, the experiments revealed to us the differences in stress strain behavior and Young's modulus for parallel timber, perpendicular timber, and aluminium. Aluminium was stronger than timber in all directions due to its isotropic nature, making it ideal for dynamic loads like bicycle frames and engine components. Timber strength did vary with grain orientation, with parallel timber being stronger and more suitable for house frames where the loads align with the grain. Errors mostly came from jaw tightness because the wood was slipping, and if we were to tighten it even more, it would crush the wood and reduce its cross section. We can improve by testing with larger cross-sectional areas to minimize growth ring effects. Further research could examine these materials under different loading rates and environmental conditions, such as temperature and humidity, for better understanding their real-world behavior. Thank you for listening. Well, if you enjoyed that video, make sure to like, comment, and smash that subscribe button. See you later, Turbinators.